All right, one more topic in our chapter on circular motion and gravitational pull. You are already familiar with this particular expression, part of Newton's second law that says that force equals mass times acceleration. We worked a lot of problems with that. You're familiar with that. And you know from what we've already talked about in this chapter that gravity is a force, and we know that that force causes acceleration on an object. And because of what we've done with free fall problems, you know that the acceleration due to gravity is on the Earth is 9.8 meters per second squared. Gravity always pulls at that particular acceleration on the surface of the Earth. So therefore, the weight that we talk about is actually a force that's exerted on the Earth. So when people on Earth discuss weight and mass, we normally use the terms interchangeably. But in physics, weight and mass are two very, very different terms. Mass refers to how much of you there actually is. Weight refers to how much the Earth is pulling on you. And so if you were an astronaut and you went to the moon, the amount of you that's there, your mass between the Earth and the moon, is not going to change. The amount of you is still there. So your mass stays constant, but your weight between here and the moon changes drastically because the moon does not pull with as much gravity as the Earth does. And so you may have heard that on the moon, you're going to weigh a whole lot less than you would on the Earth. In fact, you're going to weigh about 1/6 less on the moon, or not 1/6 less, but you're going to weigh 1/6 on the moon what you would weigh on the Earth. And that's because the pull of gravity on the moon is 1/6 that of what it is on the Earth. And so what we're going to do today is we're going to say, okay, so what does that mean as far as what weight looks like? So let's say that you weigh, or that you have a mass of 45 kilograms. That's about 100 pounds if you're a little bit more familiar with the English system of measurement. And so this is your mass, and your mass does not change according to your location. So if you're on the moon, your mass is 45 kilograms. If you're on the Earth, your mass is 45 kilograms. If you're on Jupiter, your mass is 45 kilograms. So your mass does not change according to location, but your weight does. Okay, so we said that force is the one that's due to gravity. And so the force that you're exerting on the Earth, we're actually going to call that weight now. And then your mass stays the same. And the acceleration that we're using is the one that's due to gravity. And so we're going to use a G for gravity to indicate that that's the particular acceleration that we're talking about. Okay, so weight equals mass times gravity. So let's say that you are standing on the Earth. What's your weight on the Earth if your mass is 45 kilograms? So your weight on the Earth would be 45 kilograms times 9.8 meters per second squared. So this should just look like an F equals ma type of problem, because that's really all that it is. Mass times acceleration gives me a force, except we're calling your force the weight this time. And so if I multiply that out, I will get a weight of 441 newtons. Okay, so your weight is expressed in newtons, your mass is expressed in kilograms. Now, let's say that you are, instead of being on the Earth, let's say that you're visiting the moon. And so on the moon, there's actually a different acceleration due to gravity. So on the moon, you still have a weight of 45 kilograms, but on the moon, the acceleration is 1.6 meters per second squared. Okay, so if I multiply those two numbers together, on the moon, my weight would only be 72 newtons. So you can see a very large difference here between the 72 and the 441, because the pull of gravity on the moon is so much less. So today you're going to get some practice calculating the pull of gravity and seeing how how it affects the weight of different things on some other different planets.